I'm not hearing. Lou?
Good. Okay. Thank you everyone for coming back. We really appreciate it. We're going to have a session now on the lithium-rich giants. And at the end of this session, assuming we don't have any more technical difficulties, then we'll kind of combine the panels. We thought that might work a little bit better. So Simon, go ahead and take it away.
Great, thank you. Can everyone hear me?
Yes, we can hear you.
Fantastic. All right. Good afternoon, good evening in the UK or wherever you are. It's morning here. It's about 9 a.m. Just like to thank the organizers for inviting me to give this little review of lithium-rich giants. It's a favorite topic of mine. I have to apologize in advance because it's a bit hard to compress many decades of research into 15-minute talk. So I'm gonna be missing a lot of references, probably from people in the audience. So I apologize for that. Okay, so yeah, my name's Simon Campbell. I'm from Australia. All right, so a little bit of background. I'm going to talk about normal red giant stars and what happens to lithium in those stars before we get on to the lithium-rich giants. So here I've got a little HR diagram hand sketched, main sequence in the yellow here. So here's a little main sequence turn-off star, we'll say. So on the main sequence, as we've heard, you destroy lithium in the interior, and then there'll be varying amounts left on the surface. So you have this little surface layer, which is what we observe. So let's just say this main sequence turn-off star has a lithium of 3.0. Then it becomes a subgiant branch star, and that envelope deepens, mixes up some of this gas that has 0 lithium, and so you have a dilution. And then we move on to the red giant branch proper, and that dilution continues to first dredge up where you have the maximum depth of the convective envelope. And so you end up at this lithium value of something like 1.5. And so this was predicted through models by Ibn in 1967, and he suggested an observational test would be good. And observers did this, and indeed, this dilution is very much observed. And so here's going from, again, the main sequence turn-off through subgiant branch and first dredge up. So this sort of Ibn dilution is very, very robust. So this study is of actually a global cluster, 6397 by Linda et al. 2009. You have the main sequence turn-off here. This is the CMD, subgiant branch, and the red giant branch all the way up here to higher luminosities. And this is what I'll be calling the sort of lithium HR diagram. So we have lithium reversed on the bottom versus magnitude. And so we can follow the evolution of lithium. So we have that dilution episode, then it's pretty constant along the bottom half of the RGB, but then something else happens. It starts reducing again. Models would predict it to just keep going up to the RGB tip at this constant value, sort of 1.5-ish. But we observe, at least in clusters, that this reduces very fast on the upper RGB. Now that dashed line is the location of the RGB bump in luminosity function. So it seems to turn on around the bump time and then rapidly deplete that lithium. So this started a whole industry known as deep mixing or extra mixing. Some people call it dark mixing. And there was a whole lot of theories about how you could get this extra mixing at the bottom of the convective envelope to try and deplete that lithium. Burn the lithium. Probably the most popular one these days is thermohalide mixing. And on the right here, I've got some models, again, in this HR lithium diagram. So this is using thermohalide mixing. So first we have the main sequence turn-off again, that Ibn dilution, constant, and then we have thermohalide mixing up here, which is burning it on the RGB. And you can see we get down to quite low lithium values, sort of 0 or even to -1. And so this is what we see in clusters here. So we have those two lithium depletion phases, the dilution and the burning giants. Okay. I just point out these models are actually solar mass, solar metallicity. So we have, well, I'm not sure about the mass, but certainly solar metallicity. And so if you have lithium greater than this, then you're lithium rich, of course. And this extra burning on the upper RGB doesn't affect that definition. You're still going to be rich compared to the lithium we expect up there. Okay, so that's sort of the basics of what happens in normal red giants. So we're going to focus on the lithium-rich giants now, which are the stars that buck the trend. So I've compressed 30 years of literature into one slide here. So Wallerstein and Sneeden, 1982, discovered the first lithium-rich giant. And as the decades progressed, more and more lithium-rich stars were discovered. Brown did a systematic study in 1989 and worked out that lithium-rich giants are about 1% of red giants. So they're quite a rare object, rare class of objects, and this is held up against the large surveys of today as well. On the right, I've got a plot from Kumar et al. 2011. This is sort of the game at the time. So various samples, they collected this blue sample, which is quite a nice high quality sample. They've also added in brown sample and green, and also magenta, which is other literature. So we have sort of all the lithium-rich giants of the time, and overplotted on these stellar tracks. And the tracks are color-coded. So you see red here is the RGB bump. Now this was thought to be associated with lithium enrichment at one stage. The bump through there. But Kumar et al. Pointed out that it looks like it's more closely related to the red clump or the core helium burning phase. However, the data at that stage is still not that great to confirm evolutionary phase, and certainly not to get masses. Fast forward to the present day. So we're now in the large survey era. So we have data for millions of stars. So even for these sort of rare, chemically peculiar stars, we can get quite large samples. And so in blue here on each of these studies, so this is Sarah Martel's study, 2021, 1,200 lithium-rich giants. Here's Casey, 2019, 2,000 lithium-rich giants from Lamost. And here we have 10,000 lithium-rich giants also from Lamost from Gao 2019. So you can see we've gone from knowing of about 100 lithium-rich giants to now like 10 to the 4. So it's really changed very recently. One thing you might notice in all these CMDs is that the lithium-rich giants, which are color-coded, are very much clumped around the red clump, this core helium burning phase. So that's pretty much set now. We really know that something like 80, even up to 100% in some samples are red clump stars, these lithium-rich giants. That said, there are some RGB stars that are lithium-rich. So we can see here in this plot that there's some lithium-rich giants above the clump and below, also in the glass sample in the black dots here. So it's not 100% red clump stars. Okay, so now we have this new information. We should sort of revisit this classical 1.5 Dex definition of what a lithium giant is, because most, as I just explained, most lithium-rich giants are not RGB stars, and the Ibn definition was based on RGB stars. So we need a definition that varies with evolution. And so Kirby et al. Pointed this out in 2016. So this is again clusters, and this blue line is his variable lithium-rich definition with evolution. And you can see when you get depletion on the upper RGB, that definition is getting lower and lower. And for red clump stars, because they appear just after the RGB tip, so the core helium flash up here, and then they drop down to low luminosity down here, about 50 L suns, they should have low lithium. So if you have stars that have higher lithium than that, then they should be considered lithium-rich red clump stars. This plot's from a paper a few years ago that we did. Again, it's the lithium A-star diagram. We have the main sequence turnoff here, the Ibn dilution constant. Then here we got the thermohalide mixing burning the upper RGB lithium. And you can see it gets down to very low values here. And then the core flash happens. And so the star drops down to that log L of about 1.7 or so. And so the expectation for red clump star is it's going to have very low lithium. How does this, and so this means, this is what I've been saying, is that for a red clump star, lithium rich should be higher than that RGB tip value. What does this look like compared to the observations? So this is GLAD DR2 observations, plenty of stars. As you can see, each star is a dot. This is DR2, it's getting a bit old now. So we have this main sequence turn-off value, and then we can see up here that it does seem, even at these sort of solar metallicity stars, it does seem to be a reduction on the upper RGB as well. And so the first thing we notice is that we have a whole lot of classical lithium-rich giants. I forgot to say that this horizontal band with the larger points is our red clump sample. And so you can see there's a lot, we've got a lot of red clump lithium-rich giants. But what we didn't expect was to find the bulk of the red clump stars over here at about 0.5, because this is way above the expected value at the RGB tip. This is a bit debated in the literature at the moment. It's probably a little bit more complex than this, but there might be systematic biases I'll talk about in a sec. Okay. So a classic question that comes up in this field is, okay, these stars are lithium rich, but what else is different about them? What makes them stand out? And if we can find other things that are different about them, we might be able to say something about their progenitors. So there's been a recent study by Saeed et al. 2024. So they took a sample of about 1,000 lithium-rich giants, because you can do that now, and then they paired them up with doppelgangers, so stars with exactly the same stellar parameters, metallicity as well, and they compared various properties between these doppelgangers and the lithium-rich giants. And this is the abundance result here. So they have all the elements here, and this is delta X on Fe. And so you can see immediately that there's a bit of an offset down here. These are mostly S-process elements, and so they attribute these to probable AGB pollution scenario. But I will point out the scale on the x-axis. This is all less than 0.1 dex. So these are very small effects. And most of the elements are not really doing much at all. Comparing sort of more bulk stellar parameters. So this is lithium, of course. So yellow is the lithium-rich giants. White is lithium normal. And you can see basically everything is overlain. So it's not a lot of systematic differences between these lithium-rich giants and the normal giants, doppelgangers. That said, there are some hints at things that are different, and particularly to do with line broadening, binarity, rotation, and H-alpha line profiles. So, for example, Zero Martel 2021 found that rapidly rotating stars are much more likely to be lithium-rich than slowly rotating stars, and there's more line broadening than normal stars as well. The caveat here is that this tends to be for subsets of the full lithium-rich giant samples in each of these studies. That said, we probably need more work on this. I think this is really an active area of research that needs to be continued. Okay, last two slides. So theories and scenarios. So many theories. Even from the very early days, we had planet accretion theory, AGB mass transfer, which I mentioned. Internal production, basically you want to drive the Cameron-Fowler mechanism. So you can do that through rotation-driven mixing, core helium flash-induced mixing, or other things around the RGB bump, or maybe early RGB, which is suggested about 20 years ago. Binary interactions becoming more popular, so mergers. Zhang et al. 2020 have merged RGB stars and white dwarfs, and they can make lithium-rich giants. I'm not sure how much they've compared all the other parameters with the huge amount of observations we have now, just as a cross-check. That's something that needs to be done. And also Casey et al. Suggested that tidal spin up by a binary companion might be another way to make lithium-rich giants. So that has to be investigated. Okay, so my take is that all of these probably happen at some level. It's just a matter of deciphering them. I'll skip over the summary because it's a short talk, but just focus on the future directions. So binarity and rotation activity, as I said before, these are important to be investigated in detail, and we'll need multi-epoch dedicated studies for binarity in particular. So these are long to get those longer periods. The so-called ubiquitous mild lithium enrichment at RGB tip also needs more research. Julio had a paper out saying that there may be observational biases that are leading to a false conclusion here. My jury's out on that still. Star clusters, ideal for disentangling all the problems that field samples have, of course, and I see people in the audience are working on that. That's great. And modeling, of course. Can we self-consistently produce lithium near the RGB tip? So far, it's been pretty ad hoc, and more work on mergers and binary interactions. Okay, thank you.
All right, any questions?
I'll just have a look at Slack for questions.
Right, so the question was, how many lithium-rich giants have astroseismology data where you can pinpoint their evolutionary states?
That's a good question. Actually, I'll share my screen again. Yeah, we've been focusing on this. Where's Saj, I guess. I've got a whole lot of slides that I couldn't put in. So on the right here is Malik 2023, and this is the Kepler field. So there's something like 20 lithium-rich giants in the Kepler field of that sort of order. And that has the best, of course, seismic data where you can get the mixed mode period spacing. Apart from that, there's inferred astroseismology, or there's K2, there's some tests, but getting that delta P or delta pi 1 requires very high quality data. So really the best place to do that at the moment is Kepler, and we only have small samples. I think I heard Slack go there. Is there another question? Oh, yes. So Jason's mentioned Malik 2023, which I just showed. I think Casey et al. Had something like 8 stars. But there are these large catalogs from which give you evolutionary status, but it's more inferred because you don't have the delta P.
We have another question from the room.
Okay.
Just give you this microphone. Make this easier.
Thanks. This is not a question, just a comment. We wish to note that the majority of lithium-rich giants show enhancement in sodium abundance.
Okay. So I showed that plot from. So we have sodium here. So they find a very small offset, but on average, but if you're comparing the doppelganger stars against lithium-rich giants, so they're not finding a signature in sodium there. Do you have a reference for that? Not sure why this would be a different result.
Definitely worthy of further discussion once we start having more discussions. And feel free to use the Slack channel if you want to pull people into that. Any final questions? All right. If not, thank you. And you can stop sharing your screen, Simon. We'll try and share here.
Thank you.
I know that.